Okay, so a very good afternoon, everyone. Welcome to this week 11 problem solving session on control engineering. And today we'll be discussing about state space analysis. So what we will be focusing on, uh, first of all, again, the focus is on the assignment solving. So the number one question that you have in your assignment is based on eigenvalues, right? Or like how you can go from a state space to transfer function, or even you can go from a transfer function to state space, but I don't think there is any question. But again, that's always possible. Or how you can build a state space model, right? So if you have given some dynamics of a system, how you can find a state space model, and then we will talk about state transition matrix, and again we'll talk about stability. How can we say whether a system is stable? Then we'll talk about state transition matrix and the solution of the state equation, and followed by equilibrium points, stability of equilibrium points, and that should cover linearization and so on. So you have already, I assume that you have gone through the lecture, so you know why we are doing this state space. It's the modern tool. Like as of now, we have only focused on transfer functions, and transfer functions, that's called classical control. Like there are many drawbacks. Transfer function is like it makes our analysis very, very easy. But again, like it cannot cover nonlinear systems, and it has many drawbacks. It's only valid for linear time invariant systems. So if we have time varying systems, how should we cover them? Similarly, if we have multiple input, multiple output systems, we cannot cover them based on transfer functions. Then we have to write separate transfer functions for every input, right? So that's the motivation that we go in the states, that we do the state space analysis, because it's a unified tool. We can handle linear systems, nonlinear systems, time invariant, time varying, everything, and it's fairly very simple, right? So if you have to like write any system in the state space representation, you write like this: x dot of t is equal to axt sput, y of t is equal to cx of t st of t. Right? So this is the general state space representation for any control system, where this x of t, this is called the state vector. Similarly, we have ut, this is called the input or control input. Similarly, yt, this is called output. This input is always in our control. So whenever the next week we'll be solving some problems on the observer design or the controller design. So there we will see we only have access to this output and this input, right? So we do not have full access to these states xt, right? Sometimes we are being asked to find these states xt because we are not able to measure all of these states. Similarly, sometimes the system is unstable. We are being asked to design this U such that my system state xt becomes stable. So these problems we'll be solving in the next week. But as of now, just remember that given any control system, we can always write them in this state space form. So this is a linear. So this is like how we can write a linear system, right? We'll again see that how to write non-linear system as well in this form. So as of now, just assume that this is a linear system where this A, B, C, and D, they are matrices of appropriate dimensions. The dimensions will depend on X and U accordingly, right? So any control system we can write in this form. So now let's solve one question where we will develop this model for a simple LCR circuit. So let's assume I have a circuit like this. So this is plus minus E2. This is E1, R1, L1, L2, VC, plus minus. This is C. Capacitors, the voltage is VC. And this is current I1. This is current I2. So this is given. So we have been given this circuit. So how we can write the dynamics of the system in a state space form, right? So whenever you're being asked, so the question, it's given in the question that take E1 and E2 as inputs, I1, I2, and VC as states, and VC as output. So it will always be specified, right? So whenever you are being asked to write a state space model for a system, it will always be specified that what you have to take as input, what you have to take as output, and what you have to take as states, right? So because why it's always specified, because a state space representation of a system is not unique, right? So like transfer function is unique, but no, state space representation, that's not unique. We'll see this. So now let's proceed. Let's apply KVL in this loop and then in this loop, right? So if we apply KVL in loop number 1, we can write like this: VC is equal to L1 di1 over dt plus I1 R1 plus E1, right? So this voltage drop is equal to, because current is flowing in this direction, so this will be equal to this voltage drop, and this voltage drop, right? So similarly, so let's write it. Let's simplify it a bit, so we can write it like this: di1 over dt is equal to Vc by L1 minus R1 by L1 into I1 plus, sorry, minus 1 by L1 E1, right? So minus R1 by L1 I1, VC over L1 minus L1. Okay, fine. So I wrote one equation. Why I wrote di1 over dt? Because I'm being asked to write I1, I2, and VC as states. So if I have to write them as states, I should get a differential equation. Why? Because I know the states, they are related as differential equations. So that's why I will look for some differential equation relationships for I1, I2, and VC. Right? So I've got it for I1. Similarly, apply KVL in loop 2. What you will get? What you will get if you apply KVL in loop 2, you will get L2 di2 by dt plus I2 R2 plus E2 equal to VC. Or simplifying it a bit, I can write, so I have to focus on differential equation writing. So I'll write di2 over dt is equal to minus R2 by L2 into I2 plus VC by L2 minus E2 by L2. So I got differential equation for this. I got two differential equations, so I am done with I1 and I2. Now I will write for VC. So how I can write for VC? So if you see this point, we can write KCL at this point because this I2 is going this direction, I1 is going this direction. There must be some current coming from this direction, right? Or all these currents, they are summing up to zero. So, and this current will be C dVC by dt. So I can write I1 plus I2 plus, just a second. Oh, am I audible? Hello?
Yes, sir. Yes, sir.
Okay, thank you. So uh, just this question and then we'll solve good questions. So yeah, this is another, okay, no, I'll write it properly. So we can write from this equation dVC by dt is equal to minus I1 over C minus I2 over C. So I got differential equation number 3, right? I'm done. Why I'm done? Because I only need 3 differential equations and I can write the state model. So I know my state model representation is x dot is equal to ax plus bu. So what is x dot? X dot is di1 over dt, di2 over dt, dvc over dt. So these are the 3 states and I have to write a differential of them. So this is x dot. Then I don't know what is A matrix. And what's X? X is I1, I2, and VC. Then I don't know what is B matrix, but I know my input is I1 and I2. Sorry, E1 and E2 is my input. My input is E1 and E2, right? Now, if you see equation number 1, we have 1 by L1 into VC. So di1, so I can write here 1 by L1. Then I have minus R1 by L1 I1. So I can write minus R1 by L1 I1. Then minus 1 by L1 E1. So there is no term for I2. So I will write it 0. And there is a term for E1. So E1 is here in the input. So I can write minus 1 by L1. Just let me complete this, then I'll summarize and maybe then it will be more clear because some people have joined late. Right? So this was, wait. So minus 1 over L1 and there is no term for E2. So I will write 0. Now let's look for I2. In I2 we have, wait, yeah. So in I2 we have no term for I1, so we have write 0, right? And then we have minus R2 over L2. This is for I2 and 1 over L for VC. And similarly, there is no term for E1, but there is this term for E2 that is minus 1 over L2. Similarly, if we write VC, there is 1 by C minus 1 by C for I1 minus 1 by C for I2, no term for VC, and no term for E1 and no term for E2. So let me again revise it. So the question was to find the state space model for this LCR circuit. and you're being given that take E1 and E2 as inputs, I1, I2, and VC as states, and VC as output. Right? We saw here that any control system that can be represented in state space form like this, which is given by x dot of t is equal to axt plus but yt equal to cxt plus dut. So ut is input, xt is state. So you were given this xt was given, ut was given, yt was given. The problem is to find these matrices a, b, c, and d. Right? So we have, okay, one more thing. This equation is called state equation, and this equation is called output equation. So as of now, I have only written state equation. If you see, I have only written this x dot equal to ax plus bu. I have only written state equation. So how did I write it? So in order to write this state equation, you know the state equation is a differential equation. So there will always be some dynamics. Like the system should have some dynamics. So I just wrote that in the form of KCL or KVL. So whenever you're given an LCR circuit, if you're asked to find the state space representation of that system, just write KCL and KVL and that's it. And try to get differential equations for your states. So that's what I did. I just applied KVL in loop 1 and KVL in loop 2. And for another equation, I wrote KCL. Right? So when I did KVL in loop 1, I got this equation. KVL in loop 2 got this equation. Basic, basic stuff I used. Then when I used KCL, I got this equation. So I got all the three differential equations, which I have to now accommodate in this equation. And right, accordingly, I have to find A matrix and B matrix. Right? So now, firstly, I was given states are I1, I2, and VC. So x dot will be di by dt, di2 by dt, dvc by dt, because I have to write differential of that. So I wrote that. Now this equation, this whole, all the three entries, whatever entries, these entries I wrote from this equation. So you see there is 1 over L1. So I wrote VC, like just write in a matrix form. So that's what I did. I just wrote them in the matrix form, right? And I got this representation. So I'm done. I'm done. This is x dot. This is A, X, B. This is U. So I'm done. So I wrote this x dot equal to AX plus BU. This is my state equation. Now it was given in the system. It was given in the question. Take VC as output. Take VC as output. It means my Y is VC. So can I write this Y as my Y of t is equal to I1, I2, VC plus D into U. So this I can write 0, 0, 1. So is it correct? I wrote YT as 0, 0, 1, which is 0 times I1, 0 times I2, 1 times VC, done this. Then this D will be 0. This D will be 0. 0 times U. So I was given this take this Y VC as output, then my output equation will be like this. So anybody has any doubt until here? This is very simple, very simple. So whenever you are being asked to find the state model from any circuit or from any mechanical system, the first thing that you will do is apply KCL, apply KVL, and get differential equations, and then just try to accommodate them in the proper format. So if anybody has any question, please ask. Otherwise, we'll move to his other questions. There is no such a question, I think, in your assignments based on this. But yeah, again, this is very fundamental, that how you can build a state model like of a system. So now let's solve this question. Now the other type of questions that you have, that how to find transfer function from state model. There is no direct question even based on this in your assignment, but yeah, there are some indirect questions that will be more clear. Okay, so the next part is how to find transfer function from the state model. So there's this formula. So if you are given x dot is equal to ax plus bu, just remember these equations from now onwards. They're very, very important. So if you are given x dot equal to ax plus bu, y equal to cx plus du, then the transfer function will be c into si minus a inverse into b plus du. So this is the formula that you will be remembering, and the work will be easier. Now let's solve a question based on this. Find the transfer function of the following system where x dot is equal to 0, 1, minus 2, minus 3, x plus 0, 1, u. And your y is 1, 0, x plus 0 times u. Please solve it and tell me the answer. Again, use the same formula. So I'll also solve with you. So here given, a is given as 0, 1, minus 2, minus 3. B is given as 0 and 1. So C is 1 and 0. C is, please mute yourself. Somebody has unmuted. Somebody is unmuted. And D is 0. So my transfer function will be C into Si minus A inverse into B plus du. So first of all, I'll find this Si minus A inverse. So my A is a 2 by 2 matrix. Accordingly, my I will also be a 2 by 2 matrix. So my Si will be S0, 0, S minus A. So I'll write here Si minus A is equal to 0, 1, minus 2, minus 3, which is equal to S minus 1 plus 2, S plus 3. So I got this Si minus A. Now I'll find its inverse. So my Si minus A, so I'll find its inverse. So this is a 2 by 2 matrix. The inverse of a 2 by 2 matrix is very simple. So there's a shortcut. So you just have to replace these two terms, interchange these two terms, and multiply the other two terms with minus 1, right? So, and divide by the determinant again. So the determinant is 1 into S plus 3 minus plus 2. Then this will be S plus 3. This will be S. This will be minus 2. This will be 1. Is this clear? Anybody has any doubt here? Like how I wrote this Si minus A inverse? Okay, so then you can solve this a bit. Just do one thing, yeah. Now which is equal to, now we'll multiply this with like either for C or B, like whatever is good for you. So it should be like this. 1 into S plus 3 plus 2, right? Then we have C matrix, which is 1 and 0. Then we have this minus 2 and S. Then we have B matrix, which is 0 and 1. Then we have 0. Okay, just multiply. So I'll multiply these two matrices first. So it will be 1 into S plus 3 plus 2 So this is a 1 by 2 matrix. This is a 2 by 2 matrix. So my resultant will be 1 over 2. 1 over 2 matrix. So my matrix will have 1 row and 2 columns. So it will be 1 into s plus 3 plus 0 into 2. That will be s plus 3. Then it will be 1 into 1 plus s into 0. That will be 1. Then we have 0 and 1. Again, this is a 1 by 2 matrix. This is a 2 by 1 matrix. Multiplication is feasible, and we will have a 1 by 1 matrix. So this will be 1 into s plus 3 plus 2. This will be s plus 3 into 0 plus 1. So this will be 1. So my transfer function will be 1 into, I'll just multiply s square plus 3s plus 2. So this is my required transfer function, 1 divided by s square plus 3s plus 2. Anybody has any doubt until here? Now that we have got
No, sir.
a transfer function, can now any one of you comment on the stability of this system, whether the transfer functions obtained for the system, above system, whether the system is stable or not?
Stable, sir.
How? What are the
If I find
poles?
This is
out
a
the
second order system, sir.
and
Yes, this is
poles
the
are
second
lying
one.
on left hand side.
Sorry, what are poles?
Marginally 2 plus 1. Both poles are s minus 1 and s minus 3. Poles
What are
poles will be
poles?
at minus 3 and minus 2. Minus 3 and minus 2 and minus 1.
Yes, poles will be -2 and -1. So what does it mean? Whether the system is stable or not?
System will be stable, sir. Minus 2, minus 1.
System is stable. So system is stable. Why? Because my poles are -2 and -1. They both lie in the left half plane. But again, this is a very long process. If you have to judge stability of and given a state model, you cannot do this thing that get a transfer function, then from the transfer function get poles. No. So what was the A matrix that was given? A matrix was given as 0, 1, -2, -3. So so this was my A matrix, and there were B matrix and C matrix as well. So if we are asked to find whether a system is stable and you are only given a state space model, you only have to check the eigenvalues of this matrix A, right? So you
Yes, sir.
no need to go and find the poles, because now you are in modern control. So this poles of transfer function, they are equal to eigenvalues of matrix A, eigenvalues of A. So you can see this. So how can we find the eigenvalues of matrix A? So we can, the process. So I will write 0 minus lambda, 1 minus 2 minus 3 minus lambda. So I'll find this determinant of this. So I'll find the characteristic equation. You have probably done this in your BTech first year. So this will be equal to 3 lambda plus lambda square plus 2. So if you see this equation and this equation, they're same. That's why I said poles of the transfer function and eigenvalues of matrix A, they are same. So you just check the eigenvalues of matrix A and you're done. If they are in the left half, your system is stable. If any one of them are in the right half, your system is unstable. Now please solve this question based on the above stuff. Please solve this question. Determine the transfer function if the matrices state space model or the state space matrices are given as follows. A is -3, 1, 0, -1. B is 1 and 1. C is 1 and 1, and D is 0. Also comment on the stability. also comment on the stability. Yeah, please try, because sometimes students get confused when they solve. So maybe doing 1, 2 questions will make things better. Please solve everyone. I'll write SI minus A inverse. SI minus A will be this is my SI minus A, and my SI minus A inverse will be 1 divided by S plus 1 into S plus 3. And here it will be S plus 1. It will be 1. This will be 0. And this will be S plus 3. Or can I write it like this? My SI minus A inverse, can I write it like this? It will be, I just multiply each term with this. Si plus S plus 1 into S plus 3. I multiply each of the internal terms of the matrix. So I will get 1 over S plus 3, 1 over S plus 1 into S plus 3, 0, 1 divided by S plus 1. So this is your SI minus A inverse. Now what do you need to do? You need to multiply it with B and C. Right? So my transfer function, assume that's G of S, that should be 1 and 1. 1 divided by S plus 3, 0. 1 divided by S plus 1 into S plus 3. 1 divided by S plus 1. There is 1 and 1, B matrix. And D is 0. Anyone has solved it? So let's multiply these two terms first. So it will be 1 and 1. This will be 1 divided by S plus 3 plus 1 divided by S plus 1 into S plus 3. So it will be 1 divided by S plus 3 plus 1 divided by S plus 1 into S plus 3. And here it will be 0 and 1 divided by S plus 1. Now just multiply it with 1 and 1. So this is 1 over 2. This is 2 over 2. Sorry, this is 2 over 1. So it will be 1 over 1. So my net transfer function will be S plus 1. Sorry. 1 divided by S plus 3 plus 1 divided by S plus 1 into S plus 3 plus 1 divided by S plus 1. So anybody, please solve it and find the transfer function. What will be the net transfer function? It will be, if I take S plus 1 and S plus 3 as common. So we already have S plus 3 here. So I'll write S plus 1 plus 1
Sir,
plus,
if we multiply C and SI minus A inverse first,
no
then
problem.
value
You'll get the same. You will get the same C. So that will be this is my 1 over 2 and this is 2 over 2. So I should get 1 over 2. So you should get something here and here, 1 over 2 here and here. So 1 rows, 2 columns. So you'll get 1 into s plus 1 divided by s plus 3 plus 0. So this will be this term. Then 1 divided by this whole term, big term, and then plus this term. It will be the same, I think. I think no, it's actually the same. There's no doubt. So this step, everybody understood this step? Finally, just solving it. So it will be 2s plus 5 divided by s plus 1 and s plus 3. Now tell me, what are the poles of this system, of this transfer function?
Both are negative.
Yes, both are negative, -1 and -3. So my system is stable. So anybody has any doubt how I landed here, this step, please let me know. Now there is this practice assignment question. So you're given as x dot is equal to 0, 1, 7 minus 4 into x plus 1 and 2u, y is equal to 1 and 3x. So there are no direct questions in your assignment where it's asked that find the transfer function from the state space model. But there are some indirect questions. For example, you're given a matrix and find the eigenvalue, right? Uh, or whether a system is stable or not, right? So find the transfer function and tell me. This is the last question that we'll be doing on this topic. So can you find can you find the transfer function from this model? And let me know whether that is stable or not. I'll give you options. Seven s plus 27 s square plus 4s minus 7. Option B is 7s plus 27 s square plus 4s plus 7. Option C is 7s plus 21 s square plus 4s minus 7. 7s plus 21 s square plus 4s plus 7. So please solve. If you have any doubt, let me know.
Option C, sir.
This one,
Yes, sir.
are you sure? Can you cross check?
I have just used the shortcut, sir. Then I don't know.
So which shortcut?
Like this is the form. A is the form of canonical form, sir. So
No. That's the problem. That, like, see, okay, it's not in canonical form. If you see this U matrix, is it a canonical form? What's B matrix in a canonical form? If this was 0, then no problem. But this is not 0. This is not in canonical form. So you're saying it's in controllable canonical form, right?
yes, sir. I've just check the value of A, sir. Matrix A, that is the form in the
That's fine.
canonical form.
That's fine. Yeah, that's fine. Okay. This numerator, this
Denominator
denominator
is, yes,
is
sir.
correct.
Yeah.
Denominator is correct. But what about the numerator? How can you find that? Because
I think, sir, this is the form of the C matrix, and it is a multiple of 7. If I
yes,
will common 7
true.
from the option C, then it is the form of 1 and 3. So,
That's true. You can only solve this, like you can only, this way you can only solve if you have available options.
yes, sir. Yes, sir.
Right. And yeah, we'll see that in a bit in some minutes that how can we avoid solving these long calculations? We can make use of canonical forms. Naveen has said answer is A, and indeed answer is A. So A is the correct answer. And now, can you tell me whether the system is stable or not? What are the
Obviously, not a
eigenvalues?
stable, sir, because this is a second order system, and the coefficient is like A, B, and C. C is here negative. So, for the stability, all the positive, then we can say that this is a stable system.
Yeah, what are the eigenvalues?
Complex number.
Are you sure? Let me check. I don't think, because if it is a complex number, so 7, 4, 3. Anybody else? Just find the roots of this S square plus 4 and fill. No, it will not be a complex number. Your X will be, anybody has calculated?
-2 minus root 11.
Yes, it will be actually -2 plus minus root 11. So it's not a complex number.
Yes, yes, it is a real number.
Yeah, but this one pole is in the right half.
Right
One
half.
bit
Yes,
tree
it's
one.
the unstable system.
System is unstable. The system is unstable. Is that clear to everyone? Anybody has any doubt? Otherwise, we'll move to the next topic. So is this understood, this how we can find transfer functions from the state model?
Yes, sir.
Now let's move to another topic that's called state transition matrix. State transition matrix. So how do you find this state transition matrix? For example, again, if you are given that you have a system, state space system given, y is equal to cx plus du, then how you can find the state transition matrix, right? So this state transition matrix, this is represented as phi of t. It's represented as phi of t, or it's a matrix exponential. You'll learn it in detail in the next week, maybe. And it's given as the short way, the simple way is this is equal to Laplace inverse of Si minus A inverse. So my state transition matrix is Laplace inverse of Si minus A inverse. Okay, so this is my state transition matrix. Just take the Laplace inverse of Si minus A. We have already calculated Si minus A inverse. So just taking the Laplace inverse of that, we're done. And why this is important, you'll see in a minute when we discuss the solution, right? So just do this question. There is one question probably where you're asked to find the state transition matrix. The question is, obtain the state transition matrix phi t where you are given x dot 0, 1, -2, -3. X, right? So find the state transition matrix. I think we have solved this question 0, 1, -2, -3. Yes, 0, 1, -2, -3. We have solved it. What did we find? What was our state transition matrix? Okay, let's do it again. So how should I solve it? First, I'll find Si minus A and the inverse of it, right? So my Si minus A will be, what is my Si minus A? It is S minus 1, 2, S plus 3, right? What's my Si minus A inverse? It is 1 divided by S into S plus 3 plus 2. And here it will be S plus 3, 1 minus 2S. Is this correct? Let me solve this a bit. Can I write it like this? 1 divided by S square plus 3S plus 2, right? Or can I write it like this? 1 divided by S plus 1, S plus 2. Is this correct? I just simplified it a bit. So based on this, I can just simplify this Si minus A inverse. I can write it like this. S plus 3 divided by S plus 1 into S plus 2, right? Or 1 divided by S plus 1 into S plus 2. Right, then we have minus 2 over S plus 1 into S plus 3. Then I have S into S plus 1 to S plus 3. Okay, now what should we do from here? We found Si minus A inverse, and that's this. Now what we have to do? So my state transition matrix is equal to Laplace inverse of Si minus A inverse. So I have to take the Laplace inverse of this. It means I have to take the Laplace inverse of all these individual terms, right? So what is the Laplace inverse of S plus 3 divided by S plus 1 into S plus 2? So we have read this in week number 1 or week number 2 probably. So can anybody tell me what is the procedure, how I should proceed here? So can I write it like this? A1 by S plus 1 plus B1 by S plus 2. So, or I can write it like this, S plus 3 into A1 by S plus 2.
Sir,
Uh-huh.
in the second row of Si minus A inverse matrix, why
Yes.
you are writing S plus 1, S plus 3?
Sorry. It's S plus 2.
Okay.
Thank you. Okay, so now let's proceed. So this is just the partial fraction. So if this term is 0, it means S is minus 2. If S is minus 2, this will be 1. And then B minus 2, it will be minus B. It implies my B is minus 1. Similarly, then this term is 0. It means s is minus 1. If s is minus 1, I get plus 2 is equal to 2 minus 1, 1, a1. So it means a1 is 2. So it means I can write this s plus 3 divided by s plus 1 into s plus 2 as 2 divided by s plus 1 minus 1 divided by s plus 2. Right? So now can I take the Laplace inverse of this easily? So Laplace inverse will be 2 e raised to the power minus t minus e raised to the power minus 2t. Anybody has any doubt how I wrote this?
No, sir.
So can you tell me the Laplace inverse of other terms, please? Similarly, please tell me the Laplace inverse of 1 divided by s plus 1 and 1 divided by s plus 2. Please solve it. And similarly, the other two terms, s plus 3, sorry, minus 2 divided by s plus 1 into s plus 2, and s divided by s plus 1 into s plus 2. Anyone? Simple calculation.
In 1 upon s plus 1 and s plus 2. First row, second element. So A
First
will
row, second element. Yeah, what is it?
A is equal to 1, B is equal to minus 1.
So a equal to 1. It means e raised to the power minus t, and b equal to
Minus 1.
minus 1. E raised to
Yes.
minus 2t. Okay. Similarly, please, this minus 2 divided by s plus 1 to s plus 2. And at the last, s divided by s plus 1 to s plus 2. Just tell me a and b. Fourth one I'll write. Fourth one will be
So third one is B, A is equal to 2, B is equal to minus 2.
a equals to 2, then it becomes minus, so I was minus 2 e raised to the power minus t, and b is 2.
Minus 2.
Minus 2. Minus 2,
Ah,
then it becomes this. Because there is this minus sign, right?
yes.
So then what did we get? My whole phi t, will be 2 e raised to the power minus t minus e raised to the power minus 2t, e raised to the power minus t minus e raised to the power minus 2t minus 2 e raised to the power t plus 2 raised to the power t and minus e raised to the power t plus 2 e raised to the power 2t. Right, so this is my state transition matrix for this. And we'll see shortly, this state transition matrix appears in the solution of this state space equation. So this is actually a differential equation. So this differential equation, when we solve it, we get a solution which is in terms of this state transition matrix. So if we have to find the solution of this state equation, if we have to solve for x1 and x2 or so on into x, so on up to xn, then somehow we have to solve this state transition matrix, and which is nothing but just the Laplace inverse you have to take. So again, now let's do this. This is a bit tricky. Your A matrix is given as 0, 1. You guys will solve it. I'll not solve it. 0, 1 minus 2, 0. Can you find phi t? That's the state transition matrix. Can you find it? I'll write Si minus A inverse. This is my Si minus A inverse, because Si minus A inverse, obtaining that is not a big deal. So you just have to take determinant and divide by that. But what will you do? How will you find the Laplace inverse from this onwards? Anyone? I'll give you a hint. You might make use of these two formulas. The Laplace transform of sine omega t is omega divided by s square plus omega square. Similarly, cos omega t is s divided by s square plus omega square. So make use of this and tell me the Laplace inverse of this whole matrix. And after that, we'll be getting the like phi t. Please solve it. Very simple it is. Yes, anyone? Okay, somebody has written cos 2t. Check again. Anybody? Should I solve it? So this first term will be cos of under root 2t. Sorry. Similarly, this term will be 1 over under root 2 sine of it. This is there. Okay. Root 2t. And here will be minus 2 sine of root 2t. This will be cos of root 2t. Just verify it. Just verify it. Take your time and just make use of these formulas. Might be you just have to make sure that these formulas, like they are in this form, these terms, then you might get it. So this is the answer. So now let's come to the solution, right? So this state equation is a differential equation. So if you're asked to find the solution x, so how you should proceed, right? The solution, there's a proper derivation of the solution. There might be in your lectures. So, but I've just written the last part, which is this: if this u is present, if this u is present, then the solution is Laplace inverse of si minus a inverse into x naught. So this is phi t, right? So this is state transition matrix. So in other words, I can write, so it is equal to phi t into x naught. So this is my input. If there is no, this is my solution if there is no input, right? So, but if there is if the input is present, then this term will also come into picture. That is plus phi t into b into u of s, right? So that's what I was saying, that whenever you have to find the solution of the state equation, so you need to find the state transition matrix, right? So let's do one last question based on this, then we will move towards equilibrium points and linearization. So you're given question. You're given x dot is equal to 0, 1, 0, minus 3. Please be with me and try to solve it. And this is 1, 0, u of t. And your initial condition x0, that's given out to be minus 1, 3 transpose. Right? So now, and it's given that unit step input. The input is unit step. The input is unit step. That's u of t. This is unit step. Now, first, you're being asked to find phi of t. Then also find x of t. So if before you find x of t, you need to find phi of t. So that will be used to calculate x of t, right? So let's solve it. I'll solve it quickly. So you know phi t is what? What's phi t? Phi t is Laplace inverse of si minus a inverse. So when you solve it, you will get si minus a inverse. So si minus a, this will be s0 minus 1 s plus 3. This is si minus a. And si minus a inverse, this will be this is 1 by s, 1 divided by s into s plus 3, 0, 1 divided by s plus 3. Now quickly tell me, what is the Laplace transform? This is my inverse. Now I need to take Laplace inverse of si minus a inverse. Please quickly tell me, what is the Laplace transform of 1 over s? Yes? It's 1. Similarly, what is the Laplace transform of the other term? It will be, so this is 0. The last one is e raised to the power minus 3t. And this one is 1 over 3, 1 minus e raised to the power minus 3t. So done. First part is done. We found phi t. So this is our phi t. Now we have to find xt. And xt is what? Xt is phi t into x naught plus phi t into b into u of s. Correct? So let's solve this part first. Phi t into x naught. So my phi t is 1, 0, 1 over 3, 1 minus e raised to the power minus 3t. This is e raised to the power minus 3t. And my x of 0 is minus 1, 3 transpose. So this is my 2 by 2. So I can write this as minus 1 and 3 because it's given in transpose form. Correct? So now let's multiply it. So when you multiply it, what you will get? Minus 1 into 1 into minus 1 and this into this. So it will be minus 1 plus this 3 and 3 will go. You will get 1 minus e, right, like this, minus 3t. Right? So this is your first term. And your second term is 0 into minus 1, that is 0, and 3 raised to the power e raised to the power minus 3t. Or this one and this one goes, I can write it minus e raised to the power minus 3t, 3e raised to the power minus 3t. So this was my phi t into x naught. Right? Now I need to find phi t into b into us. Right? So let's write phi t into b into us, which is equal to my phi t is 1 over 3, 1 minus e raised to the power minus 3t, 0, e raised to the power minus 3t. And what's my b? My b is 1 and 0, and my u of s is 1 over s because it's unit step. Right? So, or I can write this term as 1 over s and 0. This will be the same. Then when you multiply phi of t b u of s, it will be equal to, so you take Laplace inverse of this. So it will come out to be, let me write like this. So it will come out to be Laplace inverse of 1 over s square and 0. What is Laplace inverse of 1 over s square? Anyone? Anyone? It's a ramp signal. Please revise this. So then the complete solution, my xt is equal to phi t into x naught plus phi t into b into u of s. So this was e raised to the power minus 3t and 3e raised to the power minus 3t plus t 0, which is equal to t minus e raised to the power 3t. This is equal to 3e raised to the power minus 3t. That's my complete solution. So whenever you're asked state transition matrix, so based on the state transition matrix, you can find the solution of the state equation. So it's not, there is no question on the solution, but this is very, very important because tomorrow when you solve any control design problem or any observer design problem or any problem, not in this assignment, but there might be questions in your exam, which is the final exam based on this, because this is very, very important. Now, quickly move to the next topic that's based on equilibrium points. So when we talk about equilibrium points, normally, so these equilibrium points, they are these points, they are the resting positions of a system. What does I mean? What do I mean by this resting position? For example, if I have some system whose equilibrium point is this, then if I perturb this system by a small disturbance, so it should reach here or it should reach here. But eventually, if this is an equilibrium point, then this will again come back to this position. Right? For example, if you take an example of a pendulum. So this is the equilibrium point, one of the equilibrium points. There are many equilibrium points in case of a pendulum. So if you give some disturbance, the pendulum will reach here, then again it will reach here, but eventually it will again settle down to this original position, which is the equilibrium point. Right? So equilibrium point, this is the settling position of a system. Now there are questions where you are given a nonlinear system. Okay, now I'll tell you how we can write a nonlinear system. So this was my linear system. X dot is equal to ax plus bu, y equal to cx plus du. This was linear. So how can I write a nonlinear equation, nonlinear system? I'll write x dot is equal to f of x, right? And y is equal to h of x. So this is my nonlinear. So I can have a system like this. X dot is equal to f of x, even plus u, or it's not present, doesn't matter. Y is equal to c of x. So my output equation is linear, but my state equation is nonlinear. I can have the other way around. X dot is equal to ax, y is equal to h of x. So this is nonlinear, and this is linear. So how should we solve these nonlinear questions, nonlinear state space models? In this course, you're only concerned on linear systems, but again, if a nonlinear system is given, you will linearize it and find the corresponding linear system and then apply whatever theory you have learned. For example, if you are given a nonlinear system and you're asked, tell us whether this nonlinear system is stable or not. What you will do, you will linearize it. But where you linearize around equilibrium points. So whenever for a nonlinear system, whenever we're talking about stability, we talk about the stability of this equilibrium point, right? So because we are linearizing at this equilibrium point. We'll see this shortly. So let's do one question. And things will be more clear. Let's do one question. The question is, we're given x dot, x1 dot, x2 dot is equal to 5x1 minus 2x1 square minus 4x1 x2 and x2 minus 3x2 square plus x1 x2. So is this a linear system? Clearly, it's not a linear system. Why? Because we have this square term and we have this nonlinear term. So we cannot write this system as x dot is equal to ax plus bu, right? So, but how we can write it? Can we write it like this? We can write it x dot is equal to f of x, or I can write x1 dot is equal to f1 of x1, x2. Similarly, x2 dot is equal to f2 of x1, x2. Right? So I'm treating them differently. So this is my system. I wrote x dot is equal to f of x because I told you I've only been given this state equation. There is no output equation, right? Same things we can apply on output equation as well if that is a nonlinear equation. So for the time being, just assume that I have a system of this form, x dot is equal to f of x. So how to solve? How to solve such systems if I have to find whether this system is stable, or if I have to find equilibrium points for this system, how should I proceed, right? So what did I do? First of all, I just wrote it like this: x1 dot is equal to f of 1, f1 of x, and x2 dot as f2 of x. So what is my f1? So x1, x2 I'm not writing here. My f1 is 5x1 minus 2x1 square minus 4x1 x2. Similarly, what is my f2? My f2 is x2 minus 3x2 square plus x1 x2, right? Correct? So what should I do? If I have to find equilibrium points, I will find this f1. I'll put this f1 and 0, f1 to be 0 and f2 to be 0, and solve for x1 and x2, right? So what will I do? I'll put f1 equal to 0 and f2 equal to 0. So my f1, when it becomes 0, so what should I get? I'll get 5x1 minus 2x1 square minus 4x1 x2. So this why I'm doing this? For equilibrium points. So if I have to find equilibrium points, so I just put f1 equal to 0 and f2 equal to 0. So my f2, when I put f2 equal to 0, it will be x2 minus 3x2 square plus x1 and x2 equal to 0. Now let's name it as equation number 1, and let's name it as equation number 2. So from 1, let's solve 1 first, because there are 2 points. So equilibrium points will be something like this. So this is x1, this is x2, something like 1 comma 1. Similarly, 2 comma 1. The equilibrium points will be like this. That's why I'll be solving for these two equations, because the system is 2 by 2. So from 1, I'll write 5x1 minus 2x1 square minus 4x1 x2 equal to 0. If I take x1 common, what will I get? x1, 5 minus 2x minus 4, sorry, x1 minus 4x2 equal to 0. Correct? So it means either this x1 is 0 or this whole part is 0. So I get two things. My x1 is 0, or 5 minus 2x1 minus 4x2 is 0. Right? Similarly, from 2, if I take x2 common, from 2, if I take x2 common, so it will be x2, 1 minus 3x2 plus x1 is equal to 0. It implies either my x2 is 0 or 1 minus 3x2 plus x1 is 0. Anybody has any doubt until here? What I did, as of now, what I did, I had a nonlinear system. I broke that into x1 and x2, and then into f of 1 and f of 2. And in order for me to find the equilibrium points, I put f1 equal to 0, f2 equal to 0, right? So when I put f1 equal to 0, f2 equal to 0, I got these 4 equations, 1, 2, 3, 4. So clearly you see this f1 equal to 0, where will be, what is the value of f1? Sorry, who is this? So clearly you can see, if you put x1 and x2 both equal to 0, you will get f1 0, f2 0. See here, it will be 0, 0, 0, 0, 0, 0. So equilibrium points are those points where the value of my function becomes 0, right? So those values of x1 and x2 where my f of 1 or where the value of the function becomes 0. So clearly you can see x1 equal to 0 and x2 equal to 0 is one of the equilibrium point, but is not the only equilibrium point. There are other equilibrium points as well. So because it's a trivial solution. So equilibrium point number 1 is 0, comma 0. Now let's look for equilibrium number 2. So if you see equation number this, so let's see when x1 is 0. So when x1 is 0, you see from this equation 1 minus this equation 3x2 plus x1 is equal to 0. There are actually many ways to solve it to find the equilibrium points, and you just have to solve these two equations for all the solutions. So x1 is 0, so this goes, so 1 minus 3x2 equal to 0. It implies my x2 is equal to 1 by 3. So I got the second equilibrium point, that is when my x1 is 0, my x2 is 1 over 3. Now let's look for third equilibrium point. When my x2 is 0, then from this equation 5 minus 2x1 minus 4x2 is equal to 0. So this goes, my 5 minus 2x1 is equal to 0. It implies my x1 is equal to 5 over 2. So I got my third equilibrium point. When my x2 is 0, my x1 is 5 over 2. Right? So I got my third equilibrium point. Now let's look for fourth equilibrium point. So now I've checked all the 0 cases. Now I'll take this equation, which is the non-zero case, and this equation and solve for x1 and x2. So now let's solve these two equations. One equation is 5 minus 2x1 minus 4x2 equal to 0. And other equation is 1 minus 3x2 plus x1 is equal to 0. Right? So from this second equation, you just find the value of x1. So my x1 will be 3x2. It's high school maths. 3x2 minus 1. Just put this in this, put the value of x1 back in this equation. You will get 5 minus 2 into 3x2 minus 1 minus 4x2 is equal to 0. You solve it, it will be 5 minus 6x2 minus plus 2 minus 4x2 equal to 0. It will be minus 10x2, it will be minus 7. So my x2 will be 7 over 10. So if my x2 is 7 over 10, then my x1 is 3 into 7 over 10 minus 1. 7 3s are 21 over 10 minus 10. So my x1 will be 11 over 10. So my four equilibrium points, so I have four equilibrium points, which are 0, comma 0. The other one was 0, comma 1 over 3. The other one was 5 over 2, comma 0. The other one is 11 over 10 or 7 over 10. So this is how you find the equilibrium points. What you have to do, just put your nonlinear functions to be zero. Just find all those values for which the value of your nonlinear functions are equal to zero. So now if you check, if you put x1 as 5 over 2 and x2 as 0, you will see you will get 0. So whatever solutions we have found, they are all the equilibrium points. They're all the equilibrium points, right? Now the other question is, which among these equilibrium points is stable? Which among these equilibrium points is stable? Right? So let's put your attention. So 2 minutes, please put your attention here. So we have x dot is equal to f of x, right? This is a nonlinear system. But we only know I can find whether my system is stable or not in only if I know something like this, x dot is equal to ax. In that case, I'll just see the eigenvalues of my matrix A and I can decide whether my system is stable or not. But if I linearize this somehow, and if I can approximate this f of x as A, right? If I can somehow approximate this f of x at equilibrium points, this A, then I can get what I will get, x dot is equal to ax. And this A at particular equilibrium, I will be having some value of A for some particular equilibrium. For example, 0, 0 or 0, 1 by 3, we will say this. So then we can decide whether my system is stable or not, right? So let's see, let's try to linearize this. So what did we have? We had F1. What was F1? So F1 was 5x1 minus 2x1 squared, wait, minus 4x1 x2, and my F2 is x2 minus 3x2 squared plus x1 x2. Now see, I somehow want my A matrix. So I know my system has two states. Then what will be the order of my A matrix? If I have two states, what will be the order of my A matrix? 1, 2, 3,
2 by 2.
4. It will be 2 by 2. So I should have 4 entries in A matrix. So I know at least this thing. So now when we linearize it, so we get Jacobian, right? So that Jacobian is written like this. Why I get Jacobian? Because I have more than one state, right? So this Jacobian will be df1 over, sorry, del f1 over del x1, right? So then the second term will be del f1 over del x2. Third term will be del f2 over del x1. Fourth term will be del f2 over del x2. So now let's find this del f1 over del x1. So differentiate this with respect to x1. It will be 5 minus 4x1 minus 4x2. Is this correct? 5 minus 4x1 minus 4x2. Similarly, let's find del f1 over del x2. So I will again differentiate f1 with respect to x2. So it will be 0, then again 0, then it will be minus 4x1. Similarly, let's find del f2 over del x1. My del f2 over del x1, it will be 0, 0, and this will be x1. I hope you know how to differentiate this. Del f2 over del x2, this will be 1 minus 6x2 plus x1. If anybody has any doubt, please ask me here, because it's very important, and there are some questions of your assignment, like from your assignment based on this. So I can write this J matrix for this particular system as 5 minus 4x1 minus 4x2 minus 4x1 x2 1 minus 6x2 plus x1. Okay, this is my Jacobian. Now I need to find A matrix. So I told you A matrix, this linearization is performed at the equilibrium point. So my first equilibrium point is 0, 0. When my x is 0 and my y is 0, then what will be my A matrix? Let's just my name it as A1. So it will be, just put 0, 0 here. So this will be 5. This will be 0. This will be 0. This will be 1. I just put 0, 0, x1 and x2. So I got my A matrix. So when I know A matrix, I can find whether my system is stable or not. So can you find the eigenvalues of the system? Since this is a diagonal matrix, we know the eigenvalues are the diagonal elements. Lambda 1 is 5 and lambda 2 is 1. Both these eigenvalues are positive. They lie in the right half. So when they lie in the right half plane, what do you mean? Then what does this mean? Is my system stable or not? My system is not stable for this equilibrium point. So it means the equilibrium point 0, 0 is not stable. Can you check? Can you again check for the equilibrium point? Can you check for other equilibrium point? Let's assume 0, 1 over 3. Please tell me A2. What are the entries of this A2 matrix? For this, your A2 will be 11 over 3, 0, 1 over 3, and minus 1. Again, you will see one of the eigenvalues is in the right half. So you have an unstable equilibrium point. Similarly, for 5, 2, 0, you have A3, which is given by -5, -10, 0, 3.5. Again, right half equilibrium point, so unstable. But for the equilibrium point, which is 11 over 10, 7 over 10, you should find that your system comes out to be stable. So anybody has any doubt in this question? So let's do one again. This was for 2 dimensions. Let's do one for single dimension. So if I have a system, nonlinear system, x dot is equal to x square minus 2x. There is one similar question I think in your assignment where only one dimension is asked, and then you are being asked whether your equilibrium point is stable or not. So first I'll make you understand this question, then maybe you're able to understand the this question which I just now solved. So again, now let's see. If you have to solve what I did, what I told you, you just have this is f of x. So I will write it as x dot is equal to f of x. There is no f1, f2 because there is only one variable f. There's only one variable x. So my f of x is x square minus 2x. I have to find all those values of x where my f of x becomes 0. So I need to find x square minus 2x equal to 0. I can take x common. Then I'll get x minus 2 is equal to 0. It implies either my x is 0 or my x is 2. So if you put your x 0, you will see you'll get 0. See, if you put 0 and 2 into 0, you'll get 0. Similarly, if you put x equal to 2, you will see you'll get 0. See, if you put x equal to 2, you'll get 4, and then 2 into 2, 4. So these are the two equilibrium points for this system. Now again, how do you check? How do you check whether which among these equilibrium points is stable? So what I did in case of a 2 by 2, in case of a 2 variable system where I had 2 variables, I differentiated and I took Jacobian. Why I took Jacobian? Because there is a relationship of x1 with respect to x2. So I need to make sure, I need to see the change of x1 with respect to x2 as well. So that's why I went for del f1 over del x1, then del f1 over del x2. So I had to see change of f1 with respect to x2. Then similarly, x2 with respect to f1. But here I have only one variable. So when I have only one variable, you just need to differentiate. So here, so f of x is x square minus 2x. Just differentiate it. F dash of x is equal to 2x minus 2. Now, find f dash of x at x equal to 0. So it will be 0 minus 2. Minus 2. Find f dash of x at x equal to 2. It will be 4 minus 2 equal to 2. So this is the eigenvalue. So here in this case, the eigenvalue is negative, means this system is stable. And this is a positive system. This means the system is unstable. Is this now clear? The other one? Now you can understand the other one in a simple way. So here in this question, you only had one variable. So the system, the process is very simple for one variable. Just find the values where the f of x is 0, find those points, and at those points, find the differentiate the function, put the values of those equilibrium points, and find the eigenvalues. Since it's only one variable, the answer is eigenvalue. Similarly, for two variables, you have to find the Jacobian. So for two variables, for two variables, just remember this is the formula for Jacobian. That is, you have to see f1, you have to differentiate f1 with respect to x1, f1 with respect to x2. Similarly, f2 with respect to x1 and f2 with respect to x2. If you have three states, then it will be a 3 cross 3 matrix, f1 with respect to x1, f1 with respect to x2, f1 with respect to x3. Similarly, f2 with respect to x1, f2 with respect to x2, f2 with respect to x3, f3 with respect to x1, f3 with respect to x2, f3 with respect to x3. So I hope this is clear. So you should now be able to solve these questions where you are being asked to find the equilibrium points. So one questions is very simple. So I think there is this question, x dot is equal to x cube minus 3x. Similar to this. Just take x common. So it will be x square minus 3. Either x is 0 or x square is 0. So x square is plus minus, x is plus minus root 3. So you got 0 plus minus root 3. I think some similar question is there in your assignment. Then again, take differentiate, and put the values. See whether you're getting positive or negative. Positive, your system is unstable. Negative, your system is stable. So anybody has any doubt until here?
So there is no shortcut to calculation for this.
Where you need shortcut?
Just by going through the prediction or just by going through the differential
In which
equation.
part? Where do you want shortcut? In the calculation of eigenvalues, in the calculation of equilibrium points, or in the in order to check the stability?
In checking stability, just by observing the equation or by observing the
Which
solution of this
equation?
equation. Maybe second order system, third order system. Is there any
Yeah,
prediction?
like for equilibrium points checking or stability.
Yeah, yeah.
Stability. So for stability, you can directly see. So for example, let's assume this is -5, -1. You know these are the eigenvalues. System is stable. You can directly check if you're getting this. But you have to follow this procedure. You have to differentiate. You cannot skip that. Like differentiation, you cannot skip.
Okay, okay, okay,
Okay.
sir.
Now we have some minutes. Just there are some other questions. They are not difficult, but again, for the sake of completion, only one topic is left, well, that is canonical form. Canonical forms. So we have less time, so just go through the lectures that's defined, explained in detail, but I'll do one problem for which I'll write canonical forms, be it controllable canonical form, observable canonical form, or diagonal canonical form, right? So basically, when you go from transfer function to state space, so transfer function is unique, uh, but state space models, they are not unique. So for example, you saw this matrix, for example, in this case, so other case where okay, the first case. So by my first question, for example, in this case, let's assume I take this as first state, I2 or V2 as first state, I2 as second state, and I1 as third state. My matrix elements would be different, right? My matrix element would be different. Or if I take different inputs, not inputs, they have to be same. So if I just take different states, so my this A matrix, it will be different. So when I have a different A matrix, I have different stability, like controllability and observability, they will all change. So they are based on this A matrix only, you will see in the next lecture. So you can see this state space modeling, this is not unique like transfer function, which is unique. So now, what are some of the good forms where calculations become easy, or like you can directly make a state model from the transfer function, or if you are given a state model, you can directly write a transfer function, right? Or those forms, for example, if it is a controllable canonical form or observable canonical form, they're directly controllable or observable. You need not check. We'll see in the next week that how do we check controllability and observability. There are long calculations. But if you are given this state space directly in these forms, then you need not check. They're already controllable. So the derivation should be given in your slides. So I'll just tell you, if you are given a transfer function, how you should write it. There are questions where you are being asked to write the controllable canonical form and observable canonical form from the transfer function. So let's assume you're given the transfer function y over s into u over s, that's given as s square plus 7s plus 2. Similar example is there, s cube plus 9s square 26s plus 24. So if you have given this transfer function and you are being asked to write controllable canonical form, so how should you proceed? Very simple. So first of all, identify this. What is the order? 3. So your A matrix should be 3 by 3, right? Because this S, you already know that the poles are equal to the eigenvalues. Poles of the transfer function, they are equal to the eigenvalues of A matrix. So if poles are 3, there will be 3 eigenvalues. So it means the order is 3 by 3, right? So then how do you start? So it means you have 3 in 3. You have 3 by 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. You have 3 by 3. Now then start populating like this: 0, 1, 0. Then move one step right. So I'll write then 0, 0, 1. So if it was 4 by 4, then I will write like this: 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. I just make this pattern, just move a step right side and write this, right? So 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 this is how you start. Just identify the order and then write 0, 1, 0, 0, 0, 1. Right? Done. This is common for every question. Then what you have to do, then you have to identify this equation, the last equation, and start from the constant term and write the negative sign of this. For example, write negative 24, then negative 26, then negative 9. Right? So you just have to start from this. You just have to observe this denominator and write from the constant term and write the negative of that. So this is my A matrix. You wrote the A matrix. But you have to make sure your B matrix should be, so actually you have to write this: x dot is equal to AX plus BU. So you wrote A, X, U, everything is fixed. Your B should be zeros with respect to all these 0, 1, 0, 0, 0, 1. All for all those rows, it should be 0. So it will be 0, 0. And for the last term, for this example, it should be 1. right? 0, 0, 1. Right? Now, what should be the output matrix? Y is equal to Cx. C should be, just observe this numerator. Again, start from the constant term, write it as it is, 2, 7, and 1. This is my C. No negative sign here, right? So in order for you to write controllable canonical forms, so let's assume there is some constant here, B naught. So then here it will be B naught. But for systems like this, where there is constant term, so then you write it 0, 0, 1. Correct? And you'll have questions like this only, where there will be no multiplied term with this numerator. So in order for you to write controllable canonical form, just observe this denominator and start with writing start by writing backwards and write with the negative sign. Now, how should you write the observable canonical form? Observable canonical form is written
Sir,
from the
when there is
controllable
a in numerator, when there is a constant, so we
and
have
there
to
is a
write
constant
1, 0, 0, na sir? C matrix.
where there is when there is a
In numerator, if there is a constant,
constant where,
in
like I
numerator, in
said,
this,
B naught,
yes,
like
yes,
I said, B
yes,
naught.
numerator.
Uh-huh. Uh-huh.
So what will be the C matrix, sir? 1, 0, 0.
So do you mean multiplied with this S matrix? Let's do 2S square like this.
No, no. Instead of all these things, only constant is there. Suppose
So
24.
that constant has nothing to do with C.
Okay. But this
That
term
has to
is
do
not
with
there.
B.
Suppose this term is not there, only 24 is there.
Which term is not there?
This S square plus 7S plus 2 is suppose not there. Only constant
Okay,
term
this
is
term
there.
is not there. Then again, then that will be okay.
1,
So
0,
in
0, no?
that case, no, how you can take 1?
Yes, yes, yes.
I need to check that again, but yeah, let me see. Because I don't know, like for whether you can write this for every transfer function, because just give me a
It's sir,
minute.
it's one. He is asking about the numerator, then we will take one and then 0, 0. Because it depends on the measurement, sir. Which part we are
Yes.
measuring, like how much we are measuring. So it depends on the measurement. So at the starting, he is talking about the constant term, then constant does not affect, and we will take the 1, 0, 0. It just depend on the matrix now.
Okay. Yes. Yeah. Okay. I got it. Thank you for the clarification. So he says, yeah, that's actually correct, because see, let's assume there is no term, but we can always write 1. For example, you said there is 24. We can always write 24 into 1. This 24 will have effect in this 24 will go in B matrix. This 1 will be in the C matrix because the C is constant term, right?
Okay.
Is that what you wanted to convey, Devanand?
No, sir. It's okay, sir.
Okay. So now let's look for, okay. Let's say observable canonical form. So in case of observable canonical form, you can start from controllable canonical form. And how you can write, so again, you need to write A. So A will be, when you are done with controllable canonical form, just take this last row and write it as a column in reverse order. So I'll write it as 9 minus 26 minus 24, right? So I took last row and wrote it as column, right? Then I will take this row and write it as this 1, 0, 0. Similarly, then this row will be 0, 1, 0. This is my A matrix for observable canonical form. And for observable canonical form, my B becomes C transpose and my C becomes B transpose. Sorry, no, C is this. First, let's write B. So what will be B? B C transpose, and what is C? C is 271, and written in the opposite way. So we can write it like this: 1, 1, 7, 2. This is my B. Just take C and write it like this, and then my C will be 1, 0, 0. Right? Why C? Because I took B and then wrote it like this. So from controllable canonical form, you can always find the observable canonical form. Now, for diagonal canonical form, what you have to do, you have to make sure your eigenvalues, sorry, your poles are unique. So in this case, you have s square plus 7s plus 2 and s cube plus 9s square plus 26s plus 24. You can always write it as like, you can write it like this: s plus 2 into s plus 3 into s plus 4. Right? So you just broke down your transfer function and wrote like this, and then you can find the partial fraction, and you can find this as minus 4 over s plus 2 plus 10 over s plus 3 minus 5 over s plus 4. Right? So when your poles are distinct, then you can always write it like this, and then when doing partial fraction, you can find like this. And then my A matrix will be just diagonal elements of this. So my poles are what? Minus 2, minus 3, minus 4. So my A will be minus 2, minus 3, minus 4, 0, 0, 0, 0, 0, 0. Similarly, my B matrix will be all these constant terms. That one is minus 4, other one is 10, other one is minus 5. And my C will be x1 plus x2 plus x3. So this is my C matrix. 1, 1, 1. It will be x1 plus x2 plus, because here it will be x1, x2, x3. So when you solve it, it will be x1 plus x2 plus x3. So we are actually decoupling. We are decoupling this big transfer function into smaller transfer functions. You see, 1, 2, and 3, right? So and then we are writing like this in diagonal form. And diagonal form, it makes things very simple. Why? Because I know the diagonal elements of a diagonal matrix are the eigenvalues, and determinant is just the multiplication of them. Right? So I think like with this, we are like, the time is over, and you should now be able to solve all your assignment problems. I think we have covered state transition matrix, uh, transfer function to state space, or state space to transfer function, and equilibrium points, linearization, Jacobian, and these canonical forms, and also how we can find the eigenvalues, stability, solution of the state space equations. I think with this,
Sir,
you should now be, yes, yes.
I have watched the lectures of NPTEL.
Mm-hmm,
In form of just if diagonal form, like you're converting in the diagonal form, they have
mm-hmm.
taught us like we will take the b equals to all the values is 1, and c it depends on the different value of the after diagonal, like a and b and c.
In diagonal form, you're saying you'll take B as all 1,
Yes, sir. B
and
is
C
all
will be.
1, 1, 1. It's depend on the
Mhm,
how much matrix order, and c will
mhm.
taken as and c. That's why the fraction of the ABC is the diagonals.
Then you mean to say whatever I wrote for B, that will come in C, and whatever I wrote for B, that will come in B.
Yes, sir.
The same NPTEL lectures which are there.
Oh, sorry, sir, but
Like,
I have written, and that's why I have made the notes of that PDF. That's why.
okay, no problem. Actually, there are many other ways because I told you there are infinite ways to write these state space representations. So, like in this case, this is also correct this way, and that should also be correct, I think. Just make sure it's like if it is from that lecture, it should be correct. And I'll also verify the source and tell you the name of books where like this is given. There are many ways. Even there is one more thing when there will be repeated uh, eigenvalue or repeated pole, then you have to write it as Jordan form. There will be then Jordan block, right? And here will be 1 in that case if this is -2. So there are also those things. Just go through some books, some authentic book, and I think this will be more clear.
Sir, can you suggest any books, sir? Because I am facing lots of problem in the status space, sir. Because we are just watching, I am just watching the videos and they have not solved any questions, only the theory and theory. That's why I didn't get any concept from the videos. I'm unable to solve the question.
Okay. State space. Have you checked Ogata?
No, sure. Can you write the names, author's name?
Yeah. K Ogata, 1. And I think Norman Nice should also be fine. Somebody wrote me an email last week and asked for books as well. I don't know. I sent him books. So I have some books. You just write me an email.
Okay, sir. Okay, sir.
I have some books so which I can share. So you just write me an email on this. I'll send those books. And state space, just focus on transfer state space to transfer function. Number 1, just focus on solution, and you just need some questions. Like just find questions, even online internet. Just do like, okay, I'll write here what you need to find in this week. Other week there are some other things from state space to transfer function, or the other way around, how you should go from transfer function to state space. It's actually it comes from the concepts, like from the common sense. When you do more practice, then you can easily write from transfer function to state space, right? Just you should have good grasp on Laplace transform. This is number 1. Second thing is solution. Solution is very important. I know there are less questions in your assignment based on solution, but solution is very important, right? And you're only, I don't know whether discrete systems are discussed in the NPTEL lectures or not. Yeah, are they discussed, discrete systems, or
Sir,
only continuous systems?
discussed in the week 12, sir, about the discrete.
Okay, fine. That's fine. So there will be discrete, and for discrete, solutions are entirely different. So solution theory, then you should look for phi t, properties of phi t. That's actually the matrix exponential, right? And then these canonical forms. Canonical forms are actually important with respect to from gate perspective. So they can solve a lot of time. And in gate, normally they're like you're given uh, questions like this. So because the exams are time constrained, like students will solve from using SI minus A inverse and B. So it's not going to work. So yeah, these canonical forms. Similarly, equilibrium points. Equilibrium points with respect to this linear course, they're not important, but if you're studying a nonlinear control course, then equilibrium points are very important because they are the building blocks to study stability of a nonlinear system. Because whenever we talk whether a nonlinear system is stable or not, we talk about equilibrium points, right? And so we say this equilibrium point is stable or not, right? So yeah, this equilibrium points and linearization. This equilibrium point should cover actually. Linearization is also important. So linearization, then Jacobian and all, right? And on top of this, I would assume that you know how to write the state space equations for any system. For example, if you're given a spring mass damper system, and you should know the dynamics, and then from the dynamics, you should able to get the differential equations, and then from the differential equations, you should be able to write this in this form: x dot is equal to ax plus bu. So this is very, very important. You should start with this. Then other things will come. And yeah, I think that's it for this week. Doing until this would be sufficient. And your assignment has very, very simple problems for this week, right? So maybe some notations are weird, but I don't think questions are difficult for this week. For this question, there is one question of this form. So two questions of this form, one question of this form for equilibrium point, and I did for 2 by 2. There is no question for 2 by 2. So then similarly, you have one from modeling. You are given equations, you are given what to take initial condition or whatever. You have to write the state space model. And one question, how to write eigenvalues and eigenvectors. I think that's very simple. So for example, if you're given differential equations, you have to accommodate them in A, B, C, and D. So I think now you should be able to solve. If still you face any problem, I have given you my contact details. You can just drop over that question, or you can call me. I have shared my number as well. So then I can help you in that. With this, I'll just stop the recording. Thank you
So
very
have you
much.
shared your number?
Yes, I'll just share it again. Wait.
I am not getting it.
Oh.